Okay, so welcome to chapter 12. This is impulse responses and the real business cycle model, and this sucks. Yeah, let's just be honest with ourselves here. This really sucks. So, it cut me a little slack. It's the first time I've actually tried doing this. So, I'll tell you what. We're just gonna start this whole thing over from scratch. So, just give me like I don't know, 10 seconds or so, maybe 10 seconds. Make it 20. And we're gonna start it over.
Oh my god. Oh my god, you asshole. Are we really fucking starting this over?
Yeah, we're starting it over.
Oh my good lord. Oh Jesus. Okay, fine. Fine, I gotta go call my mother. I gotta call my brother. Fuck, I gotta call my lawyer today. You know what? Screw my lawyer. I'm not gonna call my lawyer. This is bullshit. I died in Independence Day in a giant fucking fireball, and this is what I get. Oh my god, I hate this guy.
Are we ready?
Yeah, we're ready.
Okay, cool. Let's go. And welcome to Impulse Responses in the Real Business Cycle Model, which is stuff I think from Chapter 12. It's me, Jeremy, your teacher slash wannabe radio host, I guess. I don't really know. Yeah, this is a little bit more like real and like official like and like lively. Why? Well, because I had intro music at the beginning. And you always know it's like some real shit when you have intro music at the beginning. Even if I used it without permission and the record company's probably going to sue me into oblivion. But you know what? Screw it. That's their problem, not mine as of right now. That burp brought to you by the Pepsi-Cola Corporation. Thanks, Pepsi. So let's move along here. So we're talking about impulse responses in the real business cycle model, and we're doing it while we're on NyQuil, which means we're going to have a really, really good time here. It's going to be some fun stuff. So without further ado, let's get started. Now let's talk about time series. So what is a time series? Well, I've probably covered some of the stuff with you guys before. Time series variable is just a variable that evolves over time, and it's got one observation per time period, and the ordering in this case matters. So if we were to look at, say, CPI and PCE inflation, for example, this would be a time series because there's one observation per period, and so we're looking at inflation between 1985 and 2020. So this would be a nice example of time series stuff. Hooray, let's move along. So we can do a lot of cool stuff with time series, and there's, well, sadly, a lot of cool stuff we can't do with time series, but one of the cool things that we can do with time series is play around with what's known as an autoregressive process. And this process is just an equation that runs on at least one lag of itself plus a little bit of error. It's like saying that past behavior predicts future behavior, but it doesn't do so perfectly. Now, it gets the name autoregressive, auto, because it's in terms of itself, kind of like things that you do to yourself. And it gets the term regressive because it's a regression. We're fitting a line through data. So we're trying to find a line of best fit that goes through the data that explains what the relationship is between the data and some other variable, in this case, time, how it's evolving over time. So it's a regression of a time series based on past values of itself. Now, this can be done with one lag, two lags, or really as many lags as you want, so long as the data can allow for it. You can't have more lags than you've got observations in your data set. But that's probably getting a little too far into the statistics, and I don't really want to hammer you with a lot of math, even though I immediately jump over to a page with an equation in it. I know, I'm an asshole. So I'm trying not to hammer you with too much math, but I do want you to see what some of the inner workings are. So an autoregressive, or AR for short, process looks something like this. Now, if this looks a little familiar to you, that should be because it does look familiar to you. If you remember all that stuff that I showed you with fixed points and like convergence to fixed points and all that stuff, it's just a reiteration of that, except there's a little bit of a difference, and that difference is this little epsilon t term here. Originally what I had was just y equals this alpha naught, which was our initial condition, plus this alpha 1 times yt minus 1, and this alpha 1 described what the relationship was between the lagged value and the current value. So a way that we could sort of think about that would be like going, all right, well, what is this relationship between what it was yesterday and what it is today? Another burp brought to you by the Pepsi-Cola Corporation, soon to be brought to you by Yingling Brewery. Now, the slope of this guy, if we remember, is what described the relationship between the current value and the past value. And then we got that error term, this epsilon t. So that's basically these two components here are what's known as a deterministic component of an autoregressive process. This is what can be modeled. This is what can be predicted. This is what can't be predicted. This is like the wild card of the bunch. So this guy, this is the crazy guy that, like, you know, every time you throw a party, you're like, man, if this dude shows up, I don't even know what he's gonna do. And then like this crazy guy shows up and just like shows up to the party and he's hammered, way drunker than he should be at the beginning of the party, and he like pulls his pants down or something, right? That would be the epsilon t term here. So we can get something cool from that epsilon t aside from making sure that he's on the registry for the rest of his life. And it's something known as an impulse response function. So let's say that we're moving along this autoregression process for some amount of time. So we're just kind of going for like a little road trip here, and we're moving along this AR process, and then somebody comes along and they spike that error term by some positive amount. Now that shock is going to feed through the equation, and it's causing either an increase or a decrease in y depending on what the slope of alpha 1 is. If alpha 1's positive, it's going to be an increase. If it's negative, it'll be a decrease. But if the slope, or the magnitude really of the slope, is less than 1, it will return to its original value after some time. And this is what's known as an impulse response function, and it's super useful in economics and some other fields of study. I'm not sure exactly which ones. I believe it's useful in, wow, I'm having a brain fart here. It's wonderful. Electrodynamic stuff. I believe it's useful in that. Electrical engineering. I think it's actually useful in a lot of engineering fields, but I don't really know that much about that stuff. Really, all I'm good for is economics, math, and guitar stuff. And also apparently getting sued into oblivion by record companies because I use their music without any permission whatsoever on YouTube because, yeah, I'm a rebel. Yeah. So this thing's called an impulse response function. And what it does is it looks at how this particular time series will be responding to a shock. Kind of like this. Like, I mean, here's something that's particularly shocking. At least it is to me. I mean, I wouldn't really be surprised if Paula Deen was responsible or at least involved in some way, shape, or form in the explosion and the crash of the Hindenburg. But who knows? That's just life. And here's another shock for you.
Everybody is to leave here immediately. This cafe is closed until further notice. Clear the room at once.
How can you close me up? On what ground?
I'm shocked to find that gambling is going on in here.
You're winning, sir.
Oh, thank you very much.
Best movie ever. If you don't know what the movie is, it's called Casablanca. It's from like 1942 or 43. Fantastic movie. Best film ever made. Love it. So, anyways, back to shocks. Now, it's really no surprise to anybody at this point in any of our lives that I really, really like NyQuil. I like it a lot, and I like it so much that I want to look at NyQuil consumption over time. So let's say I want to see how NyQuil consumption responds to a lot of people getting a cold. So if a lot of people get a cold, well, they're going to want to take NyQuil. So you're going to have more people wanting to take NyQuil. So if more people take NyQuil, well, is it going to keep increasing? Is it eventually going to peak? Is it going to reduce? We don't really know yet. So we're going to have to look at an impulse response function to see exactly what's happening. Now, if it does increase, it's going to increase until you see, holy shit. Okay, if you see these guys here on your wall, it's kind of time to stop drinking NyQuil. You probably had a little too much. And public service announcement from Jeremy. If you see this shit, stop drinking that shit because it's bad for you and it rots your brain. Now, enough about the pink elephants on the wall. Let's look back to impulse responses. So we have a shock to NyQuil consumption. So the quantity of NyQuil that's being purchased is going to spike. It's going to increase. And we can think about this as looking at the response over, say, 35 days. Now, on day one, people get sick. And of course, you know, because it's a cold, it's contagious, and they keep spreading it. So more and more people get sick. It'll probably stop being spread around here. But, you know, people get sick, they begin to develop and show symptoms, and then around here, NyQuil consumption peaks. Now, if we look at the percentage deviation that we're experiencing at the peak, it's just about 1/4 of a percentage point deviation from its original steady state. This green curve that we're looking at is what's known as the median impulse response draw, because what we're really doing is when we add that stochastic shock, we're using some sampling techniques and we're doing multiple draws and trying to see basically if things match, if they don't match. There's a lot of math in it. Don't worry too much about all that. This is the median draw, so this is like the middle draw. Now, we do this for every single point in time. So every single point in time that you see, let's look at the peak here. So the peak occurs at about 7.5 days. So about a week into everybody getting sick, NyQuil consumption peaks. And so at this one point in time, if you just draw a little vertical line, what you get is, here's the median. Now the mean's theoretically not going to be too far away from the median in this case. And we've got this band and this really darkly colored area. So you're probably wondering, what the hell is this? Well, if you remember statistics and you remember your confidence intervals, this is basically a 68% confidence interval. What this is that 68% of the draws that we made from the sampling distribution fall between here and here at the point in time where NyQuil consumption peaks. Now, this thicker band with a little dotted line that's not quite as heavily colored is the 95% confidence interval. So this is like saying 68% of the distribution falls here, 95% of it falls here. So really what we're saying is, or what we can gain from this, the statistical inference that we can get out of this, is that it is significant. It's a significantly positive response, both at the 68% level of confidence and the 95% level of confidence. And we know it's a significant response because these lower bands here around this impulse response function, the lower bands are above 0. So anytime you're looking at a positive response, if the lower bands here are above 0, then it's a significant response. Now, one thing that I need to make clear in terms of statistical inference, it's not exactly good form to analyze this and go, okay, well, it's going to spike and it's going to peak and then it eventually drops off and it kind of converges back towards its steady state. Because we haven't made a lot of corrections for the error in the sampling process and all that. So statistically, it's kind of bad form to explain what the shape of this thing is over time. However, if you want to think about it in an intuitive sense, go ahead and look at what it's doing over time. Just understand that, generally speaking, you want to try to find what the maximum deviation is from the steady state, whether it's a positive or a negative response. You want to know what its maximum deviation from the steady state is, and that's generally what we try to go for. There's one other thing that we'll look at when we get towards the end of this lecture, but for right now, just think about it in terms of the maximum deviation from its steady state, which here is about 0.25%. And it's a significant response or a significant deviation from its steady state because these two lower bounds on the confidence bands here are still above 0. So 95% of our draws are above 0 at the point where this consumption peaks, meaning we've got a positive and significant response. That's good. So what we can see is that consumption increases. It peaks around the time the pink elephants begin to show up. People get scared. They stop taking NyQuil, and then it begins to taper off. But this doesn't give me a lot of information beyond just what that little story is, because really when we're looking at these impulse responses, what we want is to be able to tell a convincing story, because when we're using economics, ultimately what we're doing is we're using mathematics in order to answer questions, but then as soon as we get the answers to those questions, we have to convert that the mathematical framework, we have to convert that back into English. Because if you just look at this and show somebody this, they're going to go, what the fuck are you showing me? And they're going to say that with good reason, obviously, because it's going to be like, what the fuck are you showing me, dude? Come on, really? So what you really want is to be able to try to weave an interesting story. Now, the best story that we can get out of this one is just this one line right here. Or I guess these two lines, but it's one bullet point, so it's one line, so screw it. Pink elephants show up, people get scared, they stop taking NyQuil, or conversely, they just start getting better and they don't feel the need to take NyQuil anymore, which is probably the more responsible way to conduct your businesses within your life. Now, beyond that, I don't get a lot of information. I don't get a lot of economic information because I'm looking at a change in consumption, but it's just that. It's only a change in consumption. What about the change in price for it? Any changes in demand have to have a change in price, but price doesn't show up in this response function. We have what's known as an identification problem. When we have an identification problem, we're ultimately looking for more answers than what the framework is allowed to give us, because we haven't allowed for any price stuff in this autoregressive process that we looked at that generated the impulse response function. Price didn't show up anywhere in there. It was just output or consumption, however you want to think about it. So when you have an identification problem, it's like if you've got one equation with two unknowns. You can't uniquely solve for those two unknowns because you've only got one equation. Now, if you've got two equations and two unknowns, then you can uniquely solve for both of those unknowns. In that case, that system would be identified. But if you only have one equation and two unknowns, it's under-identified. That's a problem. And that's a problem that we're going to have to try to find a way around in this case. Now, what do we do for that? How do we find our way around it? Well, first off, we ask Scooby-Doo, and he goes, "Ruh-roh, Raggy." And then we tell him to shut the fuck up because Scooby-Doo really sucked. I hated that show. And every single episode, I was hoping the ghosts would be real so they could just kill everybody in that stupid van and put them out of my misery. But it doesn't make a lot of sense to look at just one variable if we're trying to really tell an interesting story here. We're going to want to look at a couple of variables. So instead of univariate time series analysis, we're going to want to look at multivariate time series analysis, because we know that for supply and demand stuff, we need two equations, demand and supply. We can't identify two shocks from one equation at all because, well, there's the identification problem. We can't uniquely solve for two variables with only one equation. There's not enough information to be able to give us what we need to get out of this. The sniffles were not brought to you by cocaine. They were brought to you by bad pollen because I am in Savannah right now, and the pollen here is terrible. Now, this means we need to look at how two equations are going to respond if we want to look at an economic shock in the NyQuil market. So we have to have two equations, output and price. And this will give us an equilibrium in the NyQuil market. So initially, what we had was this. We're going to augment it a little bit by adding another equation and adding another variable to the first equation. So the first equation is still output, and it's in terms of the lagged values of output and also the lagged values of the price level. And then we're going to have this error term, which is going to be a little different from this because this information here regarding the price variation is going to be extracted out of this error term. So this error term is going to be a little bit smaller. Therefore, we're getting more precision in our modeling for the deterministic component, ensuring that the stochastic component, on the other hand, is giving us a better sense of what the source of shocks would be. Now, we're doing the same thing for the price level here. So the price level is dependent not just on lagged values of itself, but also on lagged values of output, and there's an error term for the price equation as well. So with these two equations, output and price, we can get an equilibrium for the NyQuil market, and we can get a set of impulse responses, which is what we would want out of this. We would get one impulse response for output, one for price. Now, the problem is output and price are endogenous to each other, because if we look at this, these two error terms here are going to be correlated with one another. Meaning, if we were to look at a set of impulse responses using this functional form right here, it's in its reduced form. Because it's in its reduced form, if you get a shock to one equation, you're going to get elements of both supply and demand shocks in both of your impulse responses, and you don't want that. You want a set of impulse responses that are uniquely identifying demand shocks and a different set that are uniquely identifying supply shocks. So we can't have this like mixture going on. We need to make sure that these two error terms are uncorrelated with each other. Hence, we're going to put it in a structural form rather than what's known as the reduced form. In the reduced form, all we're looking at are just raw correlations. But if we impose some structure to it, we can get some form of inference in terms of what the causal ordering of shocks would be. So how the fuck do we do that? Well, I'm going to tell you exactly how the fuck we do it. We first think back to microtheory. Now, in microtheory, we have to remember that demand is a function of output and price, where supply is only a function of price. Now, do you want to know what's cool about that? Just from that alone, we have enough information to put this guy into its structural form. We allow for a set of contemporaneous relationships where the demand equation is a contemporaneous function of output and price, and supply is only a function of price. So we could do this. So we estimate the reduced form. We're going to do a little bit of algebra, move some stuff around, substitute some stuff into itself, all that fun crap. And we get this. Now, these asterisks here indicate that these are structural form, both coefficients and residual terms, meaning these error terms are no longer correlated with each other because I've allowed for a contemporaneous relationship between output and price in this equation. However, here all I have is price in the contemporaneous form. Now, if I subtract this alpha naught PT from both sides, I get this. So really, this doesn't look too terribly different from what we had in the previous slide, except that I've got this contemporaneous price term in this top equation. So if we think back to what the micro theory said, demand was a function of output and price, supply is a function only of price. Well, cool. This is my demand equation now, and this is my supply equation. So I've got a dynamic demand equation and a dynamic supply equation, and from there, I can identify demand and supply shocks to the economic system. So what we have now is a structural vector autoregression, which is exactly what we wanted. Now, if we think about the static framework of this, a demand shock looks something like this. The demand curve shifts along the supply curve, which is held constant, meaning output and price move in the same direction. On the other hand, a supply shock looks something like this. Output and price move in opposite directions because the supply curve is shifting along a downward sloping demand curve that is remaining fixed. So, output and price move in the same direction for any demand shock that we see, and they move in the opposite direction for any supply side shock that we see. Write that down. I would go ahead and just pause things for right now, but you can actually just pause the video, so there's really no reason for me to stop talking. Now that I think of it, actually, this is kind of a really great way for me to lecture because I just get to keep talking, and all you have to do is just push pause on me. Excellent. Anyways, so demand side shocks, price output move together. Supply, they move in opposite directions. So if we were to look at this in a dynamic framework, if we were looking at the impulse responses, what we would see is if we got a set of impulse responses where output and price moved in the same direction, that had to be a demand shock. So this is a demand shock to the NyQuil market. We can see price is positive. It has a positive increase because at t equals 0 is the time that the shock takes place. So the impulse response function spikes up, continues to increase, and then sort of tapers off after a while. Now, this is a positive and significant increase because we can see the lower bands here are above 0, which means that we are confident at both the 68% and 95% levels that this is a positive and significant response in the price of NyQuil. Let's look at quantity for a minute. We also get a positive response in the median impulse response draw. And again, these confidence intervals are both above 0, meaning they're significant. So we get a significant response in both output and price, which is exactly what we want. Now let's look at a supply shock. Under the supply shock, we can see that at t equals 0, the price drops, but then it sort of begins to increase and kind of go back to its steady state. And the quantity, on the other hand, increases at the time of the shock, continues to increase, and then eventually it returns back down to its steady state. Again, these are significant responses because both of these confidence intervals are above 0. So we are 95% and 68% confident that this is a significant response in the price in the downward direction, and 68 and 95% confident that this is a positive response, obviously in the upward direction, in the quantity of NyQuil, which tells me, okay, cool, this is a supply shock. Good for me, I get a cookie. So we want to extend this a little bit beyond just a simple supply and demand framework. We also want to extend it to more of a general equilibrium framework like what we see in the real business cycle model. Now, in the RBC model, we looked at 3 types of shocks. We had a technology shock, a labor supply shock, and a demand shock. Now, the demand shock was triggered by one of 2 different types of shocks, either a government spending shock or a monetary policy shock. And we looked at how the economy responded to these shocks, but we did so in a static framework, not a dynamic one. With the actual model, what happens is it's a dynamic model. We can solve it out analytically, but the best way to really do it is type in the equilibrium conditions into a computer, let it solve everything out, generate data, and then impose stochastic shocks in the equilibrium and look at how everything responds. Now, the model itself will generate its own set of impulse response functions, and then we go out, we collect real-world data consistent with what the RBC model says we should be using, put it into a structural form consistent with what the RBC model suggests, and then we compare the impulse response functions. If the impulse responses match, then we have ourselves a pretty good model, and if they don't match, well, maybe there's a little bit of an issue. So we want to know if this model's any good. And we do so by comparing these impulse responses in the model to the impulse responses produced by a structural vector autoregression using real-world data. This is why we want to use a structural VAR in this particular context. It allows me to put the actual real-world data into a structural model that looks like the general equilibrium from the real business cycle model, which looks something like this. So you're probably going, holy shit, what the hell? I thought you said there wasn't going to be any math. Well, I wasn't really lying because I'm not making you do any math. I'm just showing you some math. Here we've got a number of equations that describe the equilibrium in the real business cycle model. We've got equation 1, which is the production function. We've got equation 2, which describes the consumption savings behavior over time. Equation 3 is just the investment decisions. Equation 4 is labor supply. Equation 5, labor demand. Equation 6 gives me the factor price of bonds. And then equation 7 gives me the resource constraint, which makes sure that output can't be exceeded by the sum of consumption and investment. So, okay, maybe this stuff isn't that bad, especially since you don't have to do anything with it. Now, these data can generate shocks that allow me to trace out the equilibrium conditions of the real business cycle model. So the first equation we could think of as like a supply curve, right? Output in terms of factor prices and output prices. Second gives me demand, I get consumption, investment, labor supply, blah, 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 all the stuff that I already told you. And we can use real data, an estimated VAR, to represent the equilibrium conditions of the RBC model. So what I did was a really nice thing. I went out and collected a bunch of data, and I threw it all into a VAR, and I ran my own structural vector autoregression where I imposed impulse response, or these shocks to get these impulse responses for you. Don't thank me all at once. The data come from the Federal Reserve Economic Database. They're quarterly, spanning the first quarter of 1947 all the way up to the fourth quarter of 2018. So how do we translate all this shit into a model where we can estimate it using real-world data? Well, like I said, first we got to go out and we got to gather some data. We got to get time series data on a couple of different variables. What variables? Glad you asked. They are the following. First, we've got output, which is GDP. We need something for the price level, so we're going to use the Personal Consumption Expenditures Price Index, which is the price index used by the Federal Reserve when trying to monitor inflation. We've got consumption, we have investment, the number of hours worked, I've got the real wage, the real interest rate, and the money supply. And I throw all of these into a vector autoregression, so I'm going to have an 8-equation VAR. Now, most of the impulse responses I'm going to show you aren't going to include the money supply because it's not exactly the most important variable to look at, and I don't want to hit you with too much information at once. So the money supply stuff isn't going to show up until it's absolutely necessary. So let's think about what happens in response to these shocks that we looked at in the model so far. If we remember a total factor productivity or technology shock, it originates in the production function equation. Output increases because firms can produce stuff more efficiently. Then they'll want more labor, so this technology shock is going to trigger a labor demand shock. Aggregate supply is going to shift outward, meaning output increases, prices fall. Meanwhile, this trigger in the labor demand area is going to mean hours worked and the real wage will increase, all while the real interest rate falls. Now, the real interest rate drop wasn't shown in the 4-graph system that I gave you, but just remember that it does happen in the ISLM graphs that you don't have to draw. You just kind of need to know that it falls during a supply shock and will be totally good. So let's look at what the 4-graph system predicts. This is it. The shock originates over here. The shock originates in this function, shifting the production curve up. Firms want more labor in order to produce more stuff because they can produce more efficiently. Think like getting a new toy, right? If you get this new toy, like on Christmas, and you're like, holy fuck, this toy is fucking awesome, right? you want to play with that toy a whole bunch, so you're going to need to use it a lot. Well, that's kind of what's going on here. Firms get a new toy, and they're like, oh my God, this is so cool. We want to make more of it. So they need more labor. The only way they can get people to work longer hours is to offer them higher wages. So they offer higher wages, people work longer hours, and then this leads to an increase in the aggregate supply curve, but aggregate demand doesn't change. So as aggregate supply shifts out, the price level is going to drop, and then up here we get the real interest rate reduction as well. So this is what it looks like in the static framework. So let's translate this from the static over to the dynamic framework. Well, actually, you know what? Let's not do that. Let's go over all the other shocks first. So, labor supply shock. This guy can be triggered either by an increase in the population, so like if you have like an immigration shock, for example, holding the reserve wage fixed, or a reduction in the reserve wage holding the size of the labor force fixed. This implies a shock to the labor supply equation. So the labor supply equation shifts out, hours worked will increase and the wage rate drops. But this shock did not originate in the production function, so there's going to be no shift in the production function itself. All we do is move to a new point on the existing production curve that we already have. This triggers an aggregate supply shift, but it's done by a smaller amount than what the TFP shock suggests. This is consistent with the diminishing marginal product of labor, meaning the more labor that you add to production, the less productive it gets. What do I mean by that? Well, actually, let me show you this picture. So labor supply shifts out, the wage rate drops, labor hours increase. So labor hours increase, meaning we move along this existing curve, but notice the curve, it's increasing everywhere, but it's increasing everywhere at a decreasing rate. If it were increasing at a constant rate, it would just sort of be like this straight line. If we're increasing at an increasing rate, it would do something like this. But it's increasing at a decreasing rate. The more labor you add on the margin, the less productive that labor gets. So we trace this over, and it leads up to a shift in the aggregate supply curve, but notice the shift in the aggregate supply curve is nowhere near as much as what they had in the total factor productivity shock, which was here. This is a pretty large shift for a rather not that big shift in the production function. Meanwhile, the labor supply shock, on the other hand, has no shift in the production function, and because it's upward sloping but at a decreasing rate, we're going to get a really small shift in aggregate supply. Now, let's assume that the government wants to try to spend more money to influence the business cycle. So they can either spend more through taxation or by borrowing, which means that consumers have less income to play around with and or investors have fewer loanable funds to play around with. It's likely going to be a combination of the two. Either way, the private sector has fewer units of output at their disposal. This is going to cause a shift in the IS curve, meaning the real interest rate is going to increase and the aggregate demand curve shifts out. All that you need to know out of that is aggregate demand shifts out, real interest rate goes up. Now, there's no change in technology under a shock to government spending because government isn't anywhere in the production function, and they're not considered in any of the relevant literature that anybody takes seriously to drive innovation in the production process itself. Now, a wartime case could be used as a counterexample here. I understand that. But government would have to either incentivize or mandate changes in production, which alters the resource allocation and isn't considered to be a truly exogenous shock to production. So even if the government wanted to mandate some change in production, that wouldn't show up through a change in AT, it would show up through a change in government spending still. Now, a government spending shock shifts aggregate demand, but aggregate supply is a vertical curve here. So all that happens is the price level increases and output doesn't move at all. Therefore, there's no changes in the labor markets. So employment remains exactly the same as it did before. All that happened is the price level just went up. Thanks, government. Now, let's shift gears a little bit and assume that instead of the federal government, the central bank wants to try to increase the money supply to influence the business cycle. This is a shock to the money supply curve, or the LM curve, which initially lowers the real interest rate, which shifts the aggregate demand curve out. Prices have to increase, so the LM curve actually shifts all the way back in after it shifts out. So it's kind of like a yo-yo, and the real interest rate increases back to where it was. Now, the nominal interest rate will still remain low. However, the increase in price perfectly offsets the reduction in the nominal interest rate, so the real rate remains unchanged. Prices are flexible, money is neutral, therefore there's no change to output at all. And because prices fully adjust immediately, output doesn't have to, which gives me exactly what we saw for the government spending shock. The only difference between the two is what happens to the real interest rate. Now, here's a table explaining the effects of different exogenous shocks. I've got 5 shocks here. I'm really only going to talk about 4 of them. So ignore the expected inflation shock, or the last one that we're looking at. We're going to look at the 2 supply and the first 2 demand shocks. The first supply shock was a technology shock. Output, consumption, investment, labor hours, and the real wage increase while the real interest rate and prices fall. Now, let's look over at the labor supply shock. This is a supply side shock still. So output's going to go up, prices are going to fall. Consumption and investment still increase. Labor hours go up. The real interest rate is reduced. The only difference between the two is the reduction in the real wage rate. So under the technology shock, the real wage rate increases. Under the labor supply shock, it falls. Why? Because the shock is originating inside the labor market that we're looking at, and it's a labor supply shock. So quantity, in this case hours worked, will increase, but the price level, or the real wage rate, is going to fall. That's how we can uniquely identify the difference between a technology shock and a labor supply shock from a qualitative standpoint. Now let's look at a government spending shock. Government wants to spend more money. So government spending goes up. Aggregate demand curve shifts out, price level goes up, real interest rate goes up, consumption and investment have to fall, output remains unchanged. Really what happens here is that consumption and investment will offset each other perfectly. So one might increase, the other might decrease, but the sum, as far as the percentage change between the two, will sum up to 0. So it's a little bit of a mistake on my part. Not that big a deal. Don't worry about it. It's such a small deal that I'm not even going to go back and fix this. I'm just going to tell you that I fucked up while I'm presenting this, and then that's just that. There's no change to labor markets whatsoever. Now, a money supply shock, on the other hand, is still a demand-side shock. But what happens is there's no change to output, consumption, investment, labor hours, wages, or the interest rate, and the only variable that picks up all of the slack is the price level. Now, this is an expected inflation shock. We're not going to get too far into that one. There's a little bit more stuff going on at play there. I really should have left that one out, so, well, shame on me. I'll just smack myself on the hand for it, and we're going to move on. So, now the total factor productivity shock suggests that we'll have the following set of qualitative responses. Output goes up, price level drops, labor hours worked, wage rate goes up, real interest rate drops, consumption and investment will increase. So the structure I impose on my structural VAR is consistent with this. It's a form such that output goes up, the price falls, the hours worked increase, and in addition, I require that the wage rate increases, and I want to see everything else responds. Now, why do I put those restrictions in there? Well, because I put those restrictions in there to ensure that what I'm doing is uniquely identifying an aggregate supply shock triggered by a change to technology. And then what I do is I want to see how everything else is going to respond, including these other variables after the initial restriction horizon that I require them to increase. And I plot these responses out for 24 quarters. So first, let's look at what the static response was again. So the static response was this. The output curve shifts, triggers a labor demand shock, aggregate supply shifts out, price level drops, output goes up, wages and labor hours increase, and then the real interest rate drops. So let's look here. These are the set of impulse responses. That burp was brought to you by Yingling, another company that's probably going to sue me for using them without their permission or something like that. Fuck them. So let's look at what happens here. Output increases. It increases at the time of the shock, and it continues to increase for a little while. And it does so significantly because this bottom band here is in fact above 0. So let's look at what happens here. Does output go up? Yes. Output increases. We see it here. We see it here. Okay, so that's good. We can check that one off. Price level. Well, here's 0. It drops, although it begins to sort of converge back to its steady state, but it drops and it does so significantly. So let's look at what happens over here. Does the price level drop? It does. It goes from here down to here. So far we're doing pretty good for ourselves. Consumption and investment increase because output goes up. That's kind of a given. All right, hours worked. Do labor hours increase? Yes, they do. They increase from here to here. So hours worked increased. Cool. So far, everything's working out well. Let's look at wages. The wages go up. Here, they do, in fact, go up, and then they sort of begin to taper off, but at the point of the shock, they increase and they remain positive. So even though they're falling, it's still above what its steady state was. So there was an increase in wages. Don't confuse the fact that wages are falling here with the idea that wages are negative. They're not. Wages increased, and even though they're falling towards their steady state, they're still above 0 because this is a positive percentage deviation from its steady state. So it's still above 0, and it's significantly above 0 for the remainder of the shock. Let's see what happens. Wages, yeah, they increase because wages go from here up to about here. Cool, wages increased. Awesome. And then I said the real interest rate would reduce, and it does so significantly here. So, awesome. Everything in this model matches up with what the real business cycle model suggests will happen. That's good for us. We're happy. Everything the RBC predicted actually showed up inside this set of impulse responses using real-world data. So the VAR gives me exactly what the RBC model would predict. We're pretty happy with that. I'm really happy with that. Presumably you should be happy with that too. So let's look at a labor supply shock. But before we do that, let's look at what the static response to a labor supply shock would be before we move into the dynamic framework. So the static response, remember, originates in the labor supply curve. So the labor supply curve shifts out, labor hours increase, and the wage rate drops. There's no change in technology because of this labor supply shock, so there's no technology shock occurring, meaning we just moved to a new point on the existing curve. So because there's that diminishing marginal product of labor, labor is becoming less productive at the margin as we add more and more units of labor into the production process. Therefore, the wage rate is going to fall. We trace all this stuff over and up to the aggregate supply curve. It shifts out, but it doesn't shift out by very much, meaning output doesn't increase by much and the price level doesn't fall by much. Here's the set of impulse responses consistent with a labor supply shock. We can see output increases, but it doesn't increase by very much because if we look at what we had over here, output increased by 2.5 percentage points above steady state. But if we look over here, it doesn't even increase by 1 percentage point above steady state. The price level also falls, but it doesn't fall by anywhere near as much as it does in the TFP or technology shock. Consumption and investment will increase. That's kind of cool. That's good. Hours worked increase. Well, okay, yeah, that's what we expect. We see it right here. Hours worked go from here to here. So we get a positive response in hours worked. Let's look at wages. Okay, so it looks like wages were positive here, but if you look at what this y-axis is, we see it's actually a reduction in the wage rate, and it continues to reduce, and it does so significantly because this confidence interval, both sides of the confidence interval are below 0. So for a negative response, remember, both of these guys need to be below 0, and fortunately for us, they are, because the 0 is probably right around here. So it's a significant negative response. And then the real interest rate reduces like I said it would. It falls, begins to increase again to return back to its steady state, but it falls by just shy of 2 percentage points below its steady state. So far, everything's looking pretty good. This model's doing a really good job of explaining these shocks. We're happy with ourselves. So it's like Letterkenny, like, we'll snipe Selly, boys. Yeah. Well, you have dip and ugh. Somebody should make one of these guys drink that. Because That would be really gross. I accidentally drank dip spit once, and it was one of the worst experiences in my life. I thought it was a bottle of Diet Coke, and I opened it and took a sip, and it was not Diet Coke. So let's look at how everything worked. Well, the RBC model, again, got everything right. Everything moved in the direction that we expected it to move. So far, so good. So we're happy. Like, I get like a double pat on the back and like 2 cookies because we're 2 for 2. This is awesome. This is great. We couldn't do any better than this. So let's look at a government spending shock and ask ourselves, what's the RBC model going to predict in response to a government spending shock? Well, what's going to happen is, first, government spending was an exogenous shock. I know we didn't really cover this one in that great of detail, but don't worry about it because I'm going to show you now. It causes an aggregate demand shock. And because prices are fully flexible, the LM curve, which initially the IS curve shifts out and the LM curve shifts inward, raises the real interest rate while shifting the aggregate demand curve out. So this vertical aggregate supply curve, though, output won't change. So we're using estimated data, and these error bands will theoretically be on either side of 0, meaning we won't have any significant movement in output, even though likely what's going to happen is the median impulse response draw will be either above or below 0. But it's just the variance around that, the measure of spread, is going to be so wide that we're not going to be able to make any really conclusive arguments one way or the other, meaning, well, there's not going to be any significant change in that variable. Therefore, there won't be any significant movement in output. So let's look at a demand shock that originates in the expenditure function, causing a shift in the IS curve because of government spending. Well, this is what it predicts. So all we would really see for any of these variables would just be an increase in the price level. Output won't change, labor hours won't change, wages won't change, and the real interest rate will go up. Son of a bitch. This isn't what we wanted, is it? Womp womp. No, this isn't what we wanted at all. And I identified this the way that you would identify a government spending shock. So there's an issue here. What's going on? Okay, let's look at output. Output's not supposed to increase, but it does. The price level is supposed to increase. Well, it does. Okay, cool. That works. Consumption and investment both increase. That's a bad... Ugh. That sucks. That's not good. We don't want that. Okay. Let's look at hours worked. Maybe hours worked and wages will be better. Okay, hours worked. Labor market's over here. Suggest no change. Son of a bitch. Okay, maybe wages. Maybe there's something cool. Nope. Nothing happens to wages either. Motherfucker. Okay. Well, at least the real interest rate moves in the way that it was supposed to. That's good. Now, if we look at the money supply response, okay, you can see this confidence band here is above 0. This one's below 0. This is an insignificant response in the money supply curve. This is what we should be seeing over here, over here, over here, over here, and over here. But we don't. Instead, we got fucked. That's not good. We're not happy. I'm not happy with this. Maybe you're happy. I don't know. I'm pretty pissed. This isn't good. So, did it work? Fuck no, it didn't work. And we can ask Wayne from Letterkenny just as a double check on did this work. And that's a hard no. So, shit. The RBC model didn't predict what it was fucking supposed to at all. Output goes up, the real interest rate goes up, hours worked increased, wages went up, consumption went up, investment went up. None of this shit is supposed to move the way that the data ended up showing that it did. Well, at least it predicted the real interest rate increase, so there's that. So I got at least one thing going for me. Hooray. Good. Happy me. Oh, happy day. Just kidding. God damn it. So maybe a monetary policy shock will do it instead. So let's look at a money supply shock. Well, the RBC model says the LM curve shifts out when the money supply increases, shifts the aggregate demand curve out. Prices are perfectly flexible, so when the price level has to increase, the LM curve is going to shift back in. So kind of like yo-yos, right? Goes out and then it comes back, which means money supply shock should increase demand, but output isn't going to move. So you would see an increase in price, but no change in output. Now, if you think that monetary expansion can boost output, in this model, there's no mechanism for that to happen. There's no transmission mechanism of monetary policy, meaning there's no way for monetary expansion to transmit from the nominal side of the economy over to the real side of the economy. Now, let's look at the static response. It's the exact same as what we would see under the government spending shock. All we would see here is the price level go up, and then in the ISLM stuff over here, there would be no change to the real interest rate. That's what would happen. Fuck me. This is bullshit. Okay. Output goes up here, but it wasn't supposed to. Consumption and investment go up. Well, I mean, at least that's consistent with the change in output. So that's consistent and conclusive. That's nice. Okay, cool. The price level is supposed to increase. That's good. Because, well, over here, price level goes up. We're happy. Hours worked and wages, so labor market stuff. What's going on here? Well, this says that there's a labor demand shock. How do we know that? Because hours worked increase and wages increase. Was there? Nope, there wasn't a labor demand shock. Son of a bitch. Okay, let's look at what the real interest rate was supposed to do. It wasn't supposed to change, remember, because the price level was supposed to increase by an amount that the nominal interest rate falls, leaving the real interest rate unchanged. Motherfucker. Even the real interest rate drops. This is bullshit. God damn it. Now, if this had worked in our favor, we could have a celebratory boogie that would look like this. Instead, well, it ends up looking something like this, where animal control gets called because you accidentally made this hallucinogenic crap that fucked you up, gave you bloodshot eyes, made you think that you were dancing like this, when really you're torquing upside down, and animal control gets called in hazmat suits to come try to get you, and I presumably take you to the pound. Now, for those of you that don't know what I'm talking about, allow me one moment to show you. And welcome, my friends, to the amazing world of Gumball.
Okay, so heating the copper should oxidize
You know what your problem is, Carmen? You're not even doing an experiment. You're just following orders. Where's the innovation? How can we be expected to discover new elements if you're so concerned with playing by the rules?
I'm pretty sure there are no more elements left to be discovered, Gumball.
You're forgetting the element of surprise.
Wait, what did you put in your beaker?
A dash of the unexpected, a drop of the unforeseen, and a pinch of the unpredictable.
Gumball, I take back everything I said. You're a genius.
Thank you, giant melted poodle meatball thing. You're right, my disgusting friend. This warrants a celebratory boogie.
The Amazing World of Gumball is hands down the best show, second best show on Cartoon Network, closely behind Rick and Morty. So, assuming we don't make any hallucinogenic compounds and start twerking upside down, we're going to have to assume that the monetary policy shock didn't work very well in the real business cycle model either. So what we can gather is this model doesn't do much for demand-side economics, but it works incredibly well for supply-side stuff. But don't fear for the fate of humanity just yet, because there is something interesting afoot. There's something interesting afoot, boys. Let's look at what the long-run responses to these shocks are. So if we go to the money supply shock and we look at the long-run responses, we can see everything is really trending back towards its original steady state in terms of what the real variables are. So output is trending downward. Hours worked trend downward. The real interest rate trends upward. Wages trend downward. There's a weird little spike here, but if you were to plot this out, it would eventually go back to steady state. And consumption and investment both return to their steady states as output's returning to its steady state. In addition to that, there's something even cooler. Let's look at prices for a second. So we can see prices increase, but this isn't the peak response of prices. The peak response is all the way out here. What's going on? Well, the price is increasing. It increases to a point, pauses for a minute, and then continues to increase. So what this is saying is that prices aren't exactly fully flexible, because if prices, say, spiked up to here instead of down here, what we likely would have seen is less of a response in output, which consumption and investment would respond by less, hours worked and wages would respond by less, and the real interest rate would respond by less because the price level increased enough to offset this negative response in the real interest rate and make it a little bit closer to zero. So if everything's trending towards its steady state in the long run, so if these economic variables over here are trending towards their steady states in the long run, well, maybe there's something kind of interesting going on, because we look, There's a one-time increase in the money supply. Prices increase a little bit, pause, and then continue to increase. Well, what this says is that prices aren't exactly fully flexible. They're slow to adjust. And because prices are slow to adjust, output has to respond. And because output has to respond, hours worked and wages have to increase. Because in order to make more, you need more workers. In order to get more hours worked, you have to raise the wage rate. So unemployment drops, output goes up, the real interest rate drops, which spurs investment and consumption. Okay, this is kind of cool. There's some interesting stuff here. So we can see most of these real variables, after their initial increase, begin to decrease and trend back towards zero. Meaning in the long run, or even the medium run, these real economic variables are returning to their steady states. Thus, in the medium to long run, we have monetary neutrality. So remember I told you monetary neutrality was just that a one-time increase in the money supply will lead to changes in only nominal variables, and real economic variables won't respond. Maybe a better way to think of it is a one-time increase in the money supply in the long run will lead to no real changes in economic variables. However, there could be some variability in the short run. So what does that mean? Well, it means we either need to tweak this model or we need an entirely new model. Now, this model that we need is going to have to be one that allows for demand side and or nominal shocks to have a real effect in the short run. Fortunately, we aren't the first people to think of this. People thought about this about 30 years ago, actually. And they developed the new Keynesian model, which allowed for demand shocks to have real effects. And the nice thing about the new Keynesian model is it's not that different from what the real business cycle model is. All it says is that there is, in fact, a mechanism through which nominal shocks transmit to the real economy in the short run, but not the long run, which says we can use the new Keynesian model for short-run analysis, and for long-run analysis, we can use the RBC model. This is what's known as the neoclassical synthesis. What it implies is that shit happens in the short run, but not so much in the long run, because in the long run, everything sort of returns back to its original steady state dynamic equilibrium. Now, if we allow for sticky prices, which is what we see here, prices don't fully respond immediately. They're a little sticky. They're slow to adjust, meaning they adjust over a longer run than what we initially thought they would. We allow for sticky prices, we get an entirely new range of results, which is awesome. And that's what the new Keynesian model covers. And the cool thing about the new Keynesian model, like I think I said, is it's kind of the real business cycle model, but it's like a tweak on it. So it's really just a broader class of models that includes the real business cycle model as a special case. That special case is achieved when we have fully flexible prices. The stickier prices become, on the other hand, the more of a divergence we get from the set of these impulse responses that we see using data here. This is more consistent with what we would see under a new Keynesian model rather than what we would see under the real business cycle model, all because prices are sticky. The stickier prices are, the less they respond to a shock in the short run, but the more they'll respond in the long run. The more flexible they become, the more of an increase you would see in prices initially, meaning consumption, investment, output, hours worked, wages, and the real interest rate wouldn't move by anywhere near as much as they are currently moving, as we can see using this data. Now, before we go any further, to wrap this lecture up, I want to talk about one major misconception. The real business cycle model came out in the early 1980s. All throughout the 1970s, there's a huge problem known as stagflation, in which there's high unemployment and high inflation. Now, the existing theory at the time stemmed from an older Keynesian theory that there was a trade-off between inflation and unemployment, and this trade-off was what's known as the Phillips curve. The idea was if you were to inflate the money supply, it triggers an aggregate demand shock. If prices aren't flexible, output has to increase, meaning unemployment would fall because firms need more workers in order to produce more stuff. But people figure out what's going on. They start to adjust their expectations in the real economy to these inflationary pressures. And before long, inflation doesn't really influence unemployment, at least at the rate that the central bank was inflating at. Therefore, they have to inflate even more. in which case we end up with double-digit inflation and incredibly high unemployment like what we saw with stagflation in the 1970s. Now, in the late 70s, an economist named Robert Lucas from the University of Chicago, brilliant economist, still alive, awesome dude, published a number of papers now known as the Lucas Critique. And what it stated was that really a lot of the existing economic models had massive endogeneity problems because there was no household or individual firm optimization. So the stuff couldn't be used for really any sort of policy implications whatsoever, which is why the real business cycle model came out, because it was the first attempt at making this model that fixed all of these endogeneity problems. And it did a pretty good job at it, as we can tell. It just didn't do a perfect job. Now, in the meantime, Ronald Reagan was elected in 1980, took office in 81, and when he did take office, he appointed Paul Volcker as Fed chairman. Now, Volcker aggressively cut the money supply to curb inflation, triggering a recession. He knew the recession was going to come, but it was one of those, would you rather peel the Band-Aid off or rip the Band-Aid off? He chose to rip the Band-Aid off. Once the economy responded to the shock, it went back to normal. We had low inflation and low unemployment through most of the 80s, save a couple of hiccups. Thanks, Yingling. Now, the RBC model began to pick up traction at this time because it seemed to describe the economy pretty well, and, well, there really wasn't anything else to refute it. So a lot of policies throughout the 1980s focused on supply-side factors because that's what the RBC model predicted. Now, here's where the aside gets kind of important. The RBC model was mistakenly confused with trickle-down economics or Reaganomics. Supply-side economics is not trickle-down economics, nor is it Reaganomics. All supply-side economics says is the following. A majority of variation in GDP can be described by supply-side shocks. That's it. Nothing more, nothing less. Supply-side economics says if you're looking at all the variation or all the variance in GDP over time, at least 50% plus epsilon of that can be described by supply-side shocks. An argument for demand-side economics would be a majority of the variation in GDP can be described by supply-side shocks. Now, this is an ongoing debate between macroeconomists. Is it driven more by supply-side or demand-side variables? Now, in real life, we're seeing a bunch of these shocks occur simultaneously, so you can't really just go, okay, well, it's more of this than that. So a lot of it has to do with what model you're using, the functional form that you're imposing in your autoregression or your vector autoregression models, and all of that. So it's more of a scientific argument than it is just like a political one. Because the RBC model says supply-side shocks influence the business cycle. That's all it says. It doesn't say we need to give more money to the rich to see wealth trickle down to the poor or anything stupid like that. The model and the prevailing school of thought that followed from this model were ruthlessly attacked by the media and non-economist academics because it was very heavily confused with trickle-down economics. And now there are a lot of also economist academics that attacked the model as well, but they unfortunately didn't really understand the model to the extent that they pretended to. All the RBC model says is that supply-side shocks account for more variation in GDP than demand-side shocks do. That's all that it says. Is it a potentially correct interpretation of what the real-world economic variable variance is? Maybe, maybe not. It's more likely that it's not, because it's kind of hard to make an argument purely for supply-side economics, just like it is for demand-side, because there's variation caused by shocks from both sides. Remember, supply and demand are endogenous to each other, so if you screw with one, you're going to really screw with the other, especially if one of these shocks happens to be particularly persistent. The more persistent the shock becomes, well, the more it's going to be affecting not just that one side of the economy, but also the other. For example, look at the COVID-19 case. It initially started out as a supply-side shock, but it became a very persistent supply-side shock in the form of labor demand shocks. The more persistent it became, the more it started to trigger a negative aggregate demand shock. And this is kind of this downward spiral that we're seeing in the economy right now. So it's sort of naive to say it's just one or the other. It's kind of a mixture of two. So it's like, okay, which school of thought is it? Is it a more supply side, more free market side argument, or is it more of like a demand side and like policy interventionist type argument? Well, the answer probably lies somewhere in the middle. So To wrap everything up, we tested the real business cycle model, and it seems to work really well for supply side shocks in both the short and long run, but it doesn't do so well for demand side shocks in the short to medium run. This doesn't make it a bad model. It just doesn't tell the whole story. We need to improve the model in order to tell a broader story. Hence, the New Keynesian model, or the class of New Keynesian models, really is not just one model, there's multiple models. But it's a broader class of models that can answer more questions than what the real business cycle model can. So we need this model that can allow for more short-run variation in real variables in response to demand side and nominal shocks. So we're going to discuss that in the next lecture, and we're going to talk about how it ties in with the real business cycle model, because the RBC model wasn't a bad model per se, but rather it just didn't answer all the questions that we thought it was initially going to be able to answer. So we just need a model that can answer some more of these questions instead. So with that, I bid you adieu. I say enjoy the rest of your day, your night, your whenever the hell you watch this. Enjoy the remainder of the time that you have between, when you're awake and you go to sleep. I will, of course, encourage you to stay safe, be vigilant, monitor and observe all of the quarantine and stay-at-home protocols set by the jurisdiction in which you are currently living. And I will leave you with, of course, another song that I did not get permission to play on this. So don't ever expect this to be an absolutely monetized YouTube stream. So I'm not getting anything out of this. This is me just entertaining you and I guess kind of myself in the process by listening to really awesome music. So we will be fading out, and we will end this particular lecture with Eclipse by Brand of Sacrifice. So enjoy the next minute or so of your life. You really can't get much more brutal than this. You know what? Hold on a second. I'm going to show you a little bit more Brand of Sacrifice, because why? I'm a child. That's why. Because I've mentioned pig squeals before and how awesome they are in deathcore. So I figure, you know what? What the hell? We're like a week or two away from the end of the semester, so we might as well just go ahead and wrap things up in a really fun way where I show you what pig squeals actually are. So enjoy the pig squeals. It kind of almost sounds like Cookie Monster. These aren't the pig squeals. It's just awesome. Here come the pig squeals. And with that, I say goodbye.